Inside an autonomous flight lab, a small drone is ready for a vertical test. It must rise above a 4-meter scanner but remain below a 6-meter ceiling. At launch, the chamber camera fails. One screen still shows a normalized flight curve, but that curve peaks at only 1. Can this tiny graph predict the real flight? The controller was not given a new path point by point. It was given 4 instructions: launch later, make the flight last longer, climb higher, and begin from a raised platform. The shape should survive while its position and scale change. Function transformations are the language for making one reliable shape perform a new physical job. Call the stored curve f of u equals 1 minus u squared, used only from u equals -1 to u equals 1. Think of u as normalized time. The curve begins at -1, 0, reaches its vertex at 0, 1, and returns at 1, 0. These 3 landmarks will let us track every transformation. First, add a number after the function, f of u plus d. The function produces an output, then d is added to that output. As d grows from 0 to 1, every point rises 1 unit. The input coordinates stay fixed, the vertical distances between points stay fixed, and the entire graph translates upward. Run the control backward and the graph retraces every position, +1, back to 0, then down to -1. Reverse again and it returns exactly. This undo and redo reveals what a vertical translation preserves. The curve does not become taller or wider, only its output 0 has moved. Now change the input before the function sees it. Replace u with t minus h. As h grows, the bright curve moves right. The minus sign often feels backward, but the graph is answering a precise question. Which new input t will feed an old input into f? Input transformations act before the function. Track the old vertex, which occurred at input 0. To place that vertex at new time 3, the function must receive 0 when t equals 3. The expression t minus 3 does exactly that. The inside becomes 0, 3 units to the right, so f of t minus 3 is the original graph shifted right by 3. Combine both moves, f of t minus 3 plus 1. The inside subtraction moves every input landmark right by 3. The outside addition moves every output landmark up by 1. The vertex 0, 1 becomes 3, 2. Translation changes location, not shape, and the point mapping makes that continuity visible. Translation moves a graph without changing its size. Scaling changes distances from an axis. Multiply the function output by a times f of u. As it grows from 1 to 4, every y value becomes 4 times as far from the horizontal axis. The vertex climbs from 1 to 4 while both zeros remain fixed. Let it pass through 0 and become negative. The graph flattens, then reappears across the horizontal axis. A negative output scale includes a reflection. In a lab, that can represent a position sensor wired with reversed polarity. Flip the connector back, and the trace undoes the reflection without changing its timing. For horizontal scaling, multiply the input, f of bu. Set b to 2. At new input 1/2, the function already receives the old input 1. Every landmark arrives in half the horizontal distance, so the graph compresses toward the vertical axis. The event is being played twice as fast. The factor inside and the visible width are reciprocals. Multiplying the input by 2 compresses width by 2. Dividing the input by 2 stretches width by 2, because the new clock must travel twice as far before f receives the same old input. Inside scaling changes how quickly the function explores its stored shape. Return to the flight controller. Its complete rule is g of t equals 1 plus 4 times f of the quantity t minus 3 over 2. This is one function pipeline with 4 controls: shift time by 3, stretch time by 2, stretch height by 4, and raise the whole flight by 1 meter. Follow one new time through the machine. The inside acts first. Subtract 3 to measure time relative to the middle of the flight, then divide by 2 to convert the longer real clock into normalized time U. At t equals 1, 3, and 5, F receives -1, 0, and 1. After F returns a normalized height, the outside acts. Multiply by 4 to convert one normalized height unit into 4 meters, then add 1 for the raised launch platform. The order matters. 4F plus 1 raises the scaled curve by 1, 4 times the quantity F plus 1 would raise it by 4. We can transform any landmark directly. If U, V lies on the parent graph, then the new point is 3 plus 2U, 1 plus 4V. Horizontal coordinates stretch and shift, vertical coordinates scale and shift. The parent vertex 0, 1 therefore maps to 3, 5. The parent domain from -1 to 1 maps to real times from 1 to 5 seconds. The parent range from 0 to 1 maps to heights from 1 to 5 meters. Domain follows the input transformation. Range follows the output transformation. We now know when the flight exists and every height it can reach. The scanner is at 4 meters and the ceiling is at 6. The transformed vertex gives the maximum immediately, 5 meters at 3 seconds. 5 is above the scanner and below the ceiling. Without calculating dozens of samples, the landmark map predicts that the programmed flight enters the safe measurement window. Restore the chamber camera and scrub the real clock from 1 to 5 seconds. The input converter, normalized point, transformed graph, altitude readout, and drone move together. Run backward, and every representation returns through the same states. Run forward, and the flight repeats, reaching 5 meters exactly at 3 seconds. Each control has a physical meaning. Horizontal translation is a launch delay. Horizontal scaling changes duration or frequency. Vertical scaling changes amplitude or sensor gain. Vertical translation changes equilibrium height or calibration 0. Reflection records reverse direction or polarity. The equation is compact because each symbol controls one visible feature. The same transformation language appears across physics. Shift a wave in time to represent phase delay. Scale a spring trace to change amplitude. Compress a pulse to represent a faster event. Raise a projectile graph when the launch platform moves. Calibrate a sensor by correcting its gain, offset, and polarity. One parent shape becomes a family of experiments. Keep 5 connected ideas. Outside addition shifts outputs. Inside subtraction shifts inputs in the opposite visible direction. Outside multiplication scales vertical distances. Inside multiplication scales horizontal distances by the reciprocal. Combined transformations map landmarks, domain, and range before we calculate every point. A function is not one frozen graph. It is a shape we can move, measure, and use.